Okay, so I assume some of you are familiar with Abaqus and some of you are not. So I'll try not to go into basic details. And if something is not clear, you can ask about it. But I'm assuming you are an average user of simulation software, okay? So if something is not clear, something is not understandable, you can ask the question, I'll explain it, okay? So I'm gonna be running a bit quick, and I will slow down at some points, and I will definitely slow down when you have questions to clarify. But basically, when you load Abaqus, you have this kind of interface that your colleagues already shared, and you've seen this. What's important to note is that it has some similarities to CAD softwares. There is some sort of a tree on the left. And this tree contains all the information of your simulation setup. And you can always go to any one of those and edit it by going to a manager. You can edit the data in any of those boxes or cases in the tree. What's also important is that you insert the parts by just importing them here. That's one way to do it. Always through this tree, you can do everything. You can also go to the usual method, the file import part. So this is the default, I guess, you're used to in CAD. And what you can do in Abaqus is you can go here, and by right-clicking, you can import your CAD. What's also important is that Abaqus generally doesn't have material properties. So you have to create your own material. Generally speaking, there's no list from which you choose. You just create your material, you give it a name, and you put in the data. I will show you in detail, but at least usually you should add the density. In this case, it's not important. Will you be using 1 as a density? But what we care about in this simulation is the mechanical performance. That's why we only need to simulate it as a mechanical, with mechanical properties, and just to simplify, as an elastic material without adding the plasticity deformation. So we assume that everything must remain elastic, and the stresses should not reach the stresses that induce plasticity. I assume as mechanical engineers, you understand what I'm saying. So mechanical, elasticity, and just a standard elastic material. And for that, you need the Young's modulus, so stiffness modulus or Young's modulus, which you need to find. We are printing PLA, so we need to find the stiffness modulus for PLA. So I'll call this PLA. And stiffness modulus of PLA, I usually give you minutes to search for it on your own. So for now, I'll leave it as a 1, and then maybe I'll give you some time to try to find it and see what different values you find, because that is a very important thing to discuss. And then you add the Poisson ratio, which is usually given. For now, it's safe to assume it's 0.3 or 0.31. It's not going to make a huge difference in our simulation, but it needs to be near 0.3. So 0.2 will be too non-deformable, and 0.4 will be too stiff, non-compressible. So 0.3 is a normal value for plastics in general. So at least now we created our material just by those few clicks. PLA, density 1, elastic in the list, it's a normal elastic, isotropic, Young's modulus, we need to find it, and a Poisson ratio of 3. I can click OK now, and you see here in the materials, there's PLA, and I can always right-click and go to edit. And now I'm back to the data where I want to change Young's modulus. So that it's always easy to go back to the data from this tree, so you can always find what you need. So I'm not going now into all the features. There's another way to show all the features, but just a quick example. Something else that's important is to tell the software, when you are generating your data, you're meshing, you're simulating, you should always tell Abaqus where to store that data before you even start. So you go to File and you set the work directory. So this is where Abaqus is supposed to save all your files. I already created the directory. By default, it is C temporary. So sometimes when you do this cleanup and you're cleaning your hard drive, it might delete all your files. So it's not good to keep everything in a temp folder. I created a folder in my D drive, and it's called additive 512. So I just select the folder, and if there is no folder in it, I cannot accept it. So I have to just select, click on once on the folder, and then click OK. And now I have D additive 5121. So everything I'm gonna simulate, all the files I'm gonna generate will be in this folder. This seems to be a silly thing, but actually this is a very important step that you have to do, especially if you're working on several files, several folders, a lot of data. You have to keep it organized instead of having 5,000 simulations in temp. Okay, I hope you're hearing that well. So first thing to do as a habit is always change the work directory, additive. So now we have the folder selected. And now we can talk a bit about the second important thing that is not scientifically important, but visually important. So later you're gonna save some print screens or, I don't know, take some snaps of the results, and you want to add them to a presentation, you want to add them to a report. And by default, Abaqus has a very ugly background, as you can see here. It's like dark blue going to suddenly to white with a strange transition. So for a reporting or for a nice visual pictures, it's always good by habit to go to the view graphic option, and then the viewport background, this is called the background, switch it to a solid and switch it to a white color. So in this case, you can always have a nice background that you can crop, you can clean, you can add commentary and whatever. So this seems trivial and silly, but this is important if you're generating results to be in a report or to be in a presentation. So now we're ready to start our simulation, and at least we're ready to discuss the steps of the simulation. So you see here, there's an additional menu on the top that I didn't talk too much about yet. In this, you have a drop-down menu. And if you just follow those steps, you can do everything needed to get your simulation ready and to run it. So first you have to have the part, then you generate the properties, which are the material properties and others. I will explain those. Then you assemble, if you have several parts, and you assemble the parts. But for a simulation, it's not like CAD. You're not just assembling parts, you're also assembling the forces. You're assembling other elements other than the parts. So fixing boundary condition, that's in the assembly. Adding the forces, that's in the assembly. So all the elements, gravity is in the assembly. All the elements influencing your simulation are inside that box, the assembly. Then you have adding the step. So the step is basically what kind of load you're having. Are you have a quasi-static? Do you have a dynamic? Do you have a vibration, a natural resonance frequencies? These are added in the step, which is like the type of disturbance, the type of energy that you're putting into the system. It can be a force, can be a pressure, can be electrical charge, magnetic forces, and whatever. So that's defined in the step, and I'll show you examples in a second. When you have several parts, especially in our case, in the case of the table, we need to have an interaction. So you need to define the friction forces, and you need to define the reaction forces. And there's a lot of details there. You have a dynamic friction, you have a static friction, you have a varying logarithmic friction. There's a lot of different models that you could choose from. And for example, this is something that SolidWorks or Inventor or Fusion does not usually allow you so much flexibility and so much capabilities. So those softwares, CAD softwares, give you a quick idea or a quick simple setup of a simulation. But Abaqus is a software specifically for simulation, and it allows you to use all possible tools, all possible models, and you can add those models to your assembly. I guess the load is obvious, but also in the load, there's also the fixing. So you have mirror, you have encast, like your colleague mentioned. Encast mainly means fixing, but not just when it comes to displacement. It also means fixing when it comes to rotation. So you don't have displacement along X, Y, or Z, but you also don't have any rotation along the axis X, Y, or Z. That is encast, which is like the most fixed possibility there is. I will also show you some examples quickly on that. When you're done with all of this, you have all the parts, all the properties, you have everything assembled. You told the software what kind of loading you're using, quasi-static in this case. and you add the interaction there and the loads, and now you're ready to do the meshing. So you need to add a description of the CAD model, or re-describe the CAD model into smaller elements. That is meshing itself. I assume you're very familiar with meshing from finite element modeling from your bachelor studies, or maybe your master studies now, as you have a course on finite element. So these are all the basic steps to get everything done. One more step that you will not need now, and I assume it's not generally needed, is an optimization step, where you can, as your colleague showed us a while, he had a solid model and he used the software to remove material from that solid model. So this is something you can also do on Abaqus, to do like a weight optimization, and the software will run a lot of cycles, a lot of simulation cycles, iterations, and reduce the mass, remove material with every cycle to optimize the weight of the part. So this is something you could have used for your design, and you can still use it for your design, but it is not part of our lab. It's something that you can experiment with on your own if you'd like to. When everything is done, you just need to create a job which describes everything in one file. So the job eventually ends up being a file called ENP file. It contains all the information, the material, the CAD, the property, the mesh, all the information. And you send that file to Abaqus independently, so Abaqus can calculate it. And I'll explain again a bit some details on that, how you decide the number of CPUs, the number of cores in your laptop that are calculating for the simulation. And you can also use your VGA to calculate. And there's a lot of also some small adjustments that it would be good for you to know about. When you have results, the simulation is done, you have results. This is where you load in visualization, and this is where you can analyze the results. And you can extract, plotted lines, you can extract section views, you can extract von Mises stresses, you can extract displacement along special vectors. So you can decide how to analyze the result. I think there's one microphone that's not muted. Please keep the microphones muted unless there's a question. So now that I described everything quickly, I will just do it the same way I do my simulation every day. I'll try to slow down and show you how we go forward with that. So I go by default to the part. We need to insert a part so we can create one, but we have one. So I don't need to create a part now. I just need to import it. So I right click, import, and by default, it imports the folder that I set as my work directory. So it's additive 5.1. And I see here the CAD file from Mike, and he called it 5.1 sat. Let's see if I can rename it from here. I cannot rename it from here, so I will not rename it now. But it's usually better never to send the CAD file that's called the number. So it's usually better to add some data to that file, some description. So this would be, I will rename it actually to Mike V1 at least. So I know this is the Mike file from Mike, and it's version number 1. It's even sometimes better to add some date as a reference to when was this file generated. That is very helpful for later when you're writing a report, when you're revisiting your data. This is good. So now I edited the name. It's Mike V1 5.1 2020 SAT file. So by default, when I open Abaqus and I'm importing a part, by default, it's looking for a SAT file. The reason for that is SAT is very simple as a CAD file. It's very compatible with Abaqus. But that doesn't mean that it always works. Sometimes there are some errors in the conversion of the file. And that's why I ask you to also save the file as IGS. So Mike also provided an IGS, or you can switch to STP, and Mike also provided an STP. In the list, there's also CATIA file formats if you're using CATIA. There's a general file format called Parasolid, but this is not that much compatible, generally speaking. So the best is SAT, IGS, STP. Let's go with SAT. I clicked on the file and click OK. And now it gives me a small menu. If there are several CAD files, it asks if I want to create individual parts, if it's like an assembly file. But it's very important if it is one file and it's intended to be one part, that you switch to combine into single part, and don't click on retain boundaries. In case there's some error in your CAD file, it will create an internal boundaries. So keep this off. So import all parts, combine into single part, nothing much to change. It has to be a 3D part because we're working in 3D space, and it is a deformable part. So we're not gonna change it to a rigid part. We want it to be deformable and we want it to bend. So these are default, 3D deformable. I'm not changing any of that. And in case Mike has used inches in the settings in the default units, then in some cases we need to rescale the part and divide by, I don't know, 2,554 by some, I don't know, football fields and wash machines, right, Mike? So we stay on do not scale, deformable 3D, and that's it, combined single part. Okay, now we have the CAD here. It seems all good. One important step to do before you even click anything else is to measure the part, just to be 100% sure that there was no scaling or rescaling of the part. And to measure it, before you do any work, any simulation work, you go to Tools, Query, which is like Ask, and let's look at distance. And I can zoom in on the part and select at least this area, which I expect it to be less than 6 millimeters, right? And you can see here, this is 5. So there's no units in Abaqus, and it doesn't care about units. But if I see the number 5, I know that this is now in millimeter scale, and this distance is 5 millimeters. And all data I add, for example, like displacement, if I add displacement somewhere, that should be in the units of millimeters, following the scale at which the drawing is done. So now we know our part is good, the scaling is good, nothing to do. And we have no other parts at the moment, but we need the table at least. So we still need to create the table. That is very easy, very quick. Before I do that, I'm gonna measure the opening, and I don't want the table to have any gap between this U shape and the table. It's better to have no gap. So I'll draw my table to be exactly the same width here. And that's 26 millimeters. So my table has to be 26. I'll click on distance again, and I want to measure the widths of this U shape. And this is, again, 26, is it? Could be. So Mike has designed this to be 26 in width and 26 in height. Okay, so whatever I draw as my table should be 26 millimeter thick, but I can make it 50 millimeter wide at least. That's fine. So now to create the table, I can already click here, create part, and I'll call this table. It is a 3D part. I will leave it deformable, that's fine. And it is a solid body, not a shell, not a wire or whatever. So default is okay in this case. So the moment I click continue, I get to a sketch menu. It is similar to CAD software, but Abaqus does not allow you to do too many or complicated CAD design. So it's always better to design the part in a CAD software and then bring it to Abaqus. But our table is extremely simple. So I'm gonna draw a rectangle and extrude it. So I click on the rectangle. I assume you're all very familiar with this. And you have to add the dimension here. So the table has to be 26 millimeter thick. The widths or the depths, at least maybe 50. And then I extrude it. So by clicking the middle button of my mouse, and then I click done. And then it asks how much should the depths be? Again, 50. And this should give me this block that is 50 by 50 and 26 millimeter thick. And this will be my table, which I will fix from one side, and then I will attach your part from the other side. One important small thing, but important, you see the visualization. If I try to rotate this, it always looks that there is some angles. It's not perfectly, there is some isometric view or some aesthetic, it's called here, a perspective view. So you should turn this off to see things as flat mathematical geometries without the artistic perspective. So just click here, and everything is now more geometrical engineering rather than artistic perspective. That's important when you want to see the side of the part like this, I can see the side only, but if I switch to the perspective view, I get more distortion in the lines. Anyway, that's not important now. If I want a perfect side view, I click on this menu and I can have a perfect side view. And you can rotate the part by just clicking on those and you get different sides of the same component. For now, this is not important, but this is very important later when you're analyzing results. Anyway, I have the part now. And I have here in the list two parts now, Mike's design and the table. So that's the function of this drop-down menu. And this drop-down menu here is for the models. That means how many simulation models. So I have one model here, one simulation package. If I want to, for example, keep this, and I want to do another simulation, but now with a heavier bottle, I don't need to redo all the steps. I just need to copy this. Then I'll have another model under it. So that would be like a heavy bottle, for example. Heavy bottle. And if I click OK, I have a complete copied tree that is heavy bottle with all the same information. And now I just go to the force, wherever that force is, and change it to double the value. So I can run a new simulation without destroying the old data, but I copy it. And now when I have two models, I have here in the drop-down list, two models. To keep it simple now, I'll stick to model 1, and I'll delete the heavy bottle. So we always work in the model 1 here. So it's important that you keep in mind, where are you working? So we're working in part, model 1, table. Nothing else to do. We have the two parts we need, no more parts to add. We switch to property. In property, whenever you switch, you have this long list. In part, we only needed this one so far. In properties, you generally need at least those first three. The first one is to create the material, which you already did one of them, which was the PLA. So this is the one that says, if I float, it says create material. And this is like the settings or the content of different materials. So whatever you create here is stored here. So I go to the material manager and I see whatever I created before. This is where we have PLA, and I can click edit, and then I get the menu. Okay, so here I have the material properties. So we already did this. We have PLA, and we can assign the same properties to the table. That would be okay. It wouldn't be a big deal. But we can also create the material for the table. Just to be a bit more accurate, we can create a new material called wood. Density set to 1. Elasticity elastic. I don't know what the stiffness of wood would be, but I assume maybe it's 8 gigapascal. And this is a tricky thing here. So it is gigapascal, but the model is in millimeters. There is a certain table that you can find online. If your model is in millimeter, what should be the unit or the number used for the modulus? And you will find that it should be in thousands. So 8 gigapascal, if this is a millimeter scale, it should be 8,000. Okay, so you can look the reference, you'll find it, it's easy. And you will find the description and explanation of why that is. But I'm just letting you know, if your model is in millimeter, your stiffness of 8 gigapascal should be a number of 8,000 in this box, okay? Now we go back to this. Wood is usually slightly higher. Let's keep it 35. So I'm not doing things extremely accurate here, but you can search online and find the exact Young modulus of an average table and the Poisson ratio. So we're done with this. I'm not gonna give it too much time. If we go back to manager, we see PLA and wood. So now the software knows that there are two materials that we can choose from, but I did not tell the software which of those parts is which material. So I need to assign the material to the parts. And there is a tricky step in Abaqus. I'm not sure about other simulation software, but to get to the assigning phase, you have to go through the section phase. And the section means, in this case, we have a 3D body and I have a material. So I need to tell the software first that this material is for a 3D body. And then I use that information that the material is for a 3D body. And then I tell the software that this material for 3D body is for the specific body. So I create a section and then I assign the section. I will re-explain it along the way. So I create a section. I want first this section of PLA, which is a solid, and it's a homogeneous solid. And if I click continue, it asks me which material should that be. I will again use PLA. And I click OK. Now I have a section of solid homogeneous. So it is a solid homogeneous PLA. Then I create again a section. This time let's call it wood T, wood table. It is again a solid. It's not a shell or a beam, and it's homogeneous. I'm not going to use a more complicated type, but you can see, for example, there is composite. I'm not going to go into that now. This is a bit advanced for the time available and for the content of this lab. So this is a solid homogeneous wood table. Continue, and then we select wood and click OK. So now I have again 2 sections ready that should be solid homogeneous. And now I reach the step where I tell the software that this is the CAD that should have these properties, which is the third icon here. Assign a section. I click on the part. You can give it a name, but I usually leave it default set 1. When I click done, it gives me a drop-down menu, and it asks, should this part be PLA or wood? This is the table, so I'll leave it as wood. Okay. And the color changes, so that is like a visual indicator that this part has a material assigned to it. So we're done. Now I switch back to the design from Mike, and we do the third step again. Assign section. Click on the part. Anywhere you click, you'll see it highlighted. Click done. And then we use drop-down PLA. And now, again, the color will turn green. Click done. And we have material assigned to the second part. You see, every time I do those steps, I get something called the set. And again, this is kind of something that's a bit advanced. And you will not need it now, but it is for a very more advanced assembly, where you have those sets generated and they are saved in the list. And you can use those sets later to edit. So they are here. And you can use them later to do some editing. But I'm not going to explain them now. They're not necessary. So you can just ignore them for now. We're done with the properties. You see there's more options. For example, composite layup. We're not doing any composite. There's some other assigned material orientation. So this is when you don't have a homogeneous solid. You have also some profiles, extruded geometries. You have other features. But you generally just need the beginning, and the rest is for advanced cases. I'm going to move to assembly. So we're done with part properties. Assembly is where we need to combine the parts and combine the boundary condition. By default, again, you start from the top. You have create instance, which means kind of insert the part. If you click it, you will see by default parts, and you will see the only 2 parts we have. You click on one, you can click control and click on the second. Then you have both parts ready in the assembly. And by default, they are dependent parts. So these are connected parts. They are going to be calculated together. So independent is an advanced feature that we don't need to talk about now. Nothing to change. Okay, so now you see there are 2 parts. And in this case, as in many cases, they do not properly align. So definitely, this is not our real case, right? So I need to move this to the proper position. And this is a nice thing in Abaqus. It's actually not that difficult to do that. There are 2 ways, and I will use them both. First, I want this surface here to touch the bottom of the table, or this surface here, of course, obviously, to touch the top of the table. So what I do is, I go to this feature, translate instance, meaning moving the instance. I click on the part I want to move. I click middle button. Then I tell the software that I need this dot here to be at this position. So I click on the first dot, and I click on the second dot, and it just moves to that position. So at least height-wise, it is in the right position. But you see the table is touching here. And this is, I guess, is not supposed to happen. So I will move it slightly to the right. So move it slightly away. And I need to click OK to confirm that this is the new position first. OK. And now I need to translate it laterally. And of course, it's better that the part is not exactly at the edge of the table. It would be better if I move it slightly upward or slightly to the right side. So there is no concentrated forces at the corner of the table. To do that, I again click on Translate, click on the part I want to move, click Done. But this time, instead of clicking on points, I just add vectors or displacement vectors to the new position. So you can see in the corner here, this would be the direction X, and I want to move this part more or less 10 millimeters to the back. And I want to move it maybe 1 or 2 millimeters forward along negative Z. That means I will start with my position 0. This is my starting point. I don't change this. This is 0. So I click Enter. And then I have my end point. And my end point for X, I want it to be -10 because I want it to move -10 in the direction of X. And then for Z, I again want it to be about -1 or -2. And if I click Enter, the blue part should move to the intended position. Let's see. And that's it. So you see, it moved slightly to the right, and it moved almost to the middle of the table. So it doesn't need to be exactly in the middle, but at least it should be away from this sharp corner here. Now I can click OK, and I have my parts positioned. I can use this menu to have a perfect side view. So I know exactly how they are aligned. So more or less, this is a perfect side view, but I need to turn again off the perspective. And now I can see everything from a geometrical perspective, geometrical view rather than an artistic view. So I assume this is how Mike intends his part to interact with the table. Is that right, Mike?
Yeah, that's
okay.
correct.
So this is now ready from the assembly point of view. In this menu, there's nothing more to do in this case. So you have here something like a linear pattern. You have those in CAD also, radial pattern. You have rotation, which we didn't need to do in this case. It's not that difficult to learn it on your own. You have some cases that's very important in some cases to do those merge or cut features. I assume merge is obvious what merge is. So in this case, that's it, done. We will move forward. We create a step. So a step is where you tell the software what kind of loading there is. Is it a quasi-static? Is it dynamic? Is it vibration? And again, you have a long list. So you switch to step, you have a list, and you start from the top going down. Here you have the action taken, and here you have the storage of those actions. So we start by the first one, creating a step. By default, you have always something called the initial step. So that is what happened before. Maybe you do the load or whatever. So this is like a setup initial step where there are no forces yet. And now we create something after it, after the initial. By default, it's called step, but we can call it load the bottle. Okay, so it's good sometimes to add some name so you know what that is. And by default, this is a static general. And you see in the list of options, there's a long list. So you have something called dynamic, implicit, explicit, thermal, electrical, structural. You have visco, soil, mass diffusion, heat transfer. It's a long list. But the default, what we're doing now is static general. And even in this, you have a drop-down menu for linear perturbation where you have frequency, whatever, resonance, and all other things. So we stay with the default. You don't need to change anything. General, static general. And you just click continue. And now that you're creating this step, which will be called load the bottle, you can add more description to it and say, oh, this bottle, this is just a description, this bottle of 1 kilogram. This simulation will run as if it's being done in 1 second. So the time period of this loading will be 1 second. As long as we're not adding acceleration and we're not adding inertia, it doesn't matter how fast or slow you do the loading if there is no inertia, there's no momentum, there's no acceleration. So this is quasi-static, so it will ignore momentum, it will ignore inertia. And in case you have buckling in your structure, depending on your design, I think in Mike's case, there will be no buckling. There is mostly bending and twisting. You don't need to turn this on. So I'm not going to explain in detail what NLGOM is, but this is a feature that is useful or more useful when you have a buckling. Maybe in the case of Awal's design, there will be buckling. So it's better to turn it on. This will increase the length of the simulation. So they will take much more time to calculate, but it will have less errors if you have buckling. By default, for now, you can turn it on. These simulations are relatively small. They take maybe 20 to 30 to maybe 1 hour time. So that is fine. In case you have friction, and in this case, you do have friction, it is advised to have some dissipation, some energy absorption to dissipate or to stabilize the displacement. So it's good at least to add a bit of either dissipated energy fraction or damping factor. They are more or less similar. So you can leave it by default, add a bit of energy dissipation. And I don't know if you're ever familiar with simulation, you need some stabilization effect. And that's why you need those energy dissipation. So of course, we don't have any adiabatic heating effects. We're not going to add this. So we leave it off. I didn't change anything except those two. But there is also this incrementation step that's very important. By default, the incrementation size, which means the first calculation time, would be 1 second. So our default total time is 1 second, and our first calculation step is 1 second. That means the software will try to calculate everything into one step. And that means it's gonna, bite more than it can chew. You should never leave it as 1, especially for a relatively complicated simulation like this, because you have friction, you have forces and interaction. So by default, this should be 1/100 over your time period. So if this is 1 second, the first initial incrementation should be 0.01. These are general recommendations. So at least you should switch incrementation to 0.01. And the software tries first to calculate for 0.01 second of your total time of 1 second. And then when that works, it will calculate for another 0.1, and it will try to recalculate and keep calculating until it reaches, the 1 second time. If the simulation is running well, it will calculate a step of 0.01, but then the next step will be 0.02. And then another step will be 0.05. So we'll try, as long as it's stable, it will try to increase the step size and increase the time calculated, so it will run faster. If it sticks to 0.01, if it remains at 0.01, obviously you will need 100 increments. If it reaches some problems, it will try to automatically reduce this number. So the software will take care of this and try to reduce this to much smaller time steps. So it will go maybe to 0.01. And in that case, you will need 10,000 steps to reach the 1 second. So the software will automatically adjust depending on how stable the simulation is. So the default is 0.01. The default here is 100, but again, it's a habit that to increase this to 1,000. In case 0.1 is not enough, and in case it goes to smaller numbers, it will need more than 100 increments. It will need 1,000 or even more. So at least 1,000, and in some cases, 10,000. So, but it doesn't hurt to make this number larger. So this is where the software will stop and tell you, oh, I cannot reach my result. So it doesn't hurt to add this number, but if you make it too big, the software might run for 5 years and never reach the result. So, and this is the minimum size it will go to. So the initial would be 0.1. The minimum is 1 to the power minus 5, which is 4 zeros after the comma, and a maximum of 1. Again, as a safe habit, it's okay to change this to the power minus 8. So whatever I'm showing you now is the minimum you should do to get a decent simulation running. And the other, there's a lot of data there. You can read 4 books about what you see here. So I'm not going to explain all of that. But I assume if you did any FEM or you studied FEM, maybe you have an idea what full Newtonian is, quasi-Newtonian. You have a solver, unsymmetric, symmetric. You have a direct simulation, iterative. So these are theoretical methods to do FEM. And I'm not going to go into that. I'm just going to say the default is more than enough for what we're doing. Okay. So that's it for the step. And please keep in mind, the step is very important. So we're done. And now I can go to again to the manager, and I see I created the step that's called load the bottle. It's a static general. We have an LGOM on, and the time period is 1 second. So you can always review what you have done by going to the manager. Whatever you see here is not necessary. So this is where you add something called feed output settings and a history output. And this is where you ask the software to, for example, calculate the stress at a very specific point. And then it will create a table with the stress values at that point. So this is where you request very specific data to be calculated. By default, you do not need to edit any of that. So if I click now on the manager, there is already field output created automatically. And if I click edit, you'll see a list of data that automatically is requested, including stresses, strains, forces, and whatever. And you don't need to adjust any of that. So that is called the field output. There's also the history output. I will not explain too much now the differences, but also the history output, in this case, that would be energy. And this is other values of energy that's generated by the force. So when you add the bottle and the bottle is pushing down, you're stressing the structure. That means you're putting energy into the structure. And this data, this value of energy is calculated at every second or every step of second. Nothing much to explain, but this is something for advanced applications. We go to interaction. So this is again important. In our case, we need to have friction between the table and the part. Again, you follow this list and you can always check on it here. Whatever you see here is not necessary for basic mode or for whatever we're doing now. This is advanced. So we stick with those. We start with the create interaction. So we want to create an interaction between the parts. By default, this is called initial interaction 1. You can call it friction whatever, table, friction table. And by default, it's at the step already that is load the bottle. But this list is not complete, or it is missing some options. If you are in the step already, you should switch it to initial. And when you switch to initial, you get one extra option and you get some other options. But what we care about is this extra option, which is called the general contact. And that means you do not need to tell the software which surface is interacting with which other surface. The software will identify automatically where there are interactions or where there are contact. So you just switch to initial and you select general contact standard. And now again, continue. We get a menu and it says all with self. And that means, for example, if this part bends too much until it touches itself again, it will also have a contact and it will also have friction with itself. So that's why by default, this is all with self. And what is missing is the property assignment. So how much is the friction coefficient? And this list is empty. We don't have a friction coefficient assigned. So we click here, interaction property, and we create the friction. And by default here, you have a contact. So we can call this, I don't know, plastic. So this is a plastic wood friction. I'm going to use kind of a safe value or an approximative value. We didn't measure the friction between PLA and the table we have. So by default, this is contact, not fluid or whatever, fluid exchange or whatever, other options. We stay with the contact, standard, plastic wood, continue. It's an empty menu. As I said, Abaqus doesn't have generally a library. So we have a tangential friction. It's not frictionless, so we switch to penalty. There is, again, static kinetic, rough, Lagrange, whatever. The default, usually the basic friction is the penalty with a friction coefficient. For this case, 0.1 is very, let's say, safe. You could reduce it, but 0.1 is reasonable. It actually can be a bit slightly lower, but that is fine. And what is important to also consider is you don't only have a tangential contact, you also have a normal contact. So that means not just a parallel, but perpendicular. And you have to set it as default. It's a hard contact. That means this part mechanically or physically is not diffusing into the other part. So if you have here a sponge and the table is made of butter and you're pressing the sponge down, the sponge will go into the butter. And that is a different type of a normal behavior. Okay, so the default is a hard contact. You have something exponential, linear, tabular, and whatever. The default is that these materials do not diffuse into each other. So hard default. So that's what you need for the contact. Please keep that in mind, tangential and normal. And by default, you allow separation. That means this is very important also. If this part is gonna lift off, if this edge wants to lift off, you want to allow separation, okay? So when I click OK, I now have in my list something that I can use, plastic wood, and everything else's default is fine. For this case, there's a lot of more options that we don't need to discuss now. And I click OK. Now I can go here. I have a friction table created. So it is created for initial, and it is propagated for load. That means all the description here is again used for the load case. Nothing to discuss here. We also have the plastic wood interaction as a contact. That is when I created the interaction property. So this is the second menu, but I got to the second menu through the first one. Here I got, so this button, interaction property, and you can see the logo, is the same button here. So that's why I didn't click this. I already did it here. I'm gonna move a bit faster now. So this is for the friction interaction. For the bottle, so now I have a contact between the part and the table, but where does the bottle go? So I'm not gonna draw a bottle and put it and apply forces. I could, but it's not necessary. I assume the bottle is not going anywhere. I assume there's a constant friction in that location. To do that, I need to create a point, and you can see here there's something called the reference point. And I don't need to have it exact, but I need to approximate it. It's better to have it somewhere here where the bottle should be. So I'm gonna try to find a location for it. So I can go to Tools, Query, Point Node, and I click on this point here, the lower point, so to find the coordinates. And if I click here, I will find those coordinates, which are the coordinates of this point. And I want to shift almost to the middle, right? So I want to shift back on Z. And that means this final value of Z minus 75, I know the bottle is 26 or 25 in diameter, so I want to shift about 12 millimeter Z. That means my minus 75, I have to add 12 to it. It's gonna be 63, so minus 63. So now I know where my reference point should be. Exact coordinates as those, except Z should be about 63 or 63.5. It doesn't matter, it doesn't need to be exactly in the center. I will explain in a second why. So now I got the data, I select this data here, and I click Control Copy. So I'm just copying those coordinates. And I go to this, create reference point, and I paste here those coordinates. And then I change the Z value to 63.5. And I hope I'm not wrong. Now, if I click Enter, I should see a dot in the center. There is one, but it's too yellow, and the background is white. If I click here, I assume you can see it. So it says reference point 1, and there's the X. And now I can rotate a bit the view. You see where the location of that point is. And this is where I will apply the force of the bottle. So we're done with this interaction. We created the reference point. Now I just need one last step in the interaction. I need this entire surface. I assume that the bottle is applying a force on this entire surface, which is not completely accurate, but it is a safe assumption. I can even make it a bit worse. Maybe I will make it a bit worse. No, let's leave it simple. That will complicate things and it's unnecessary. So I need to couple this entire surface to this point. So if I apply 10 newtons here, that 10 Newton will be distributed on this surface. And this is the third option here, create a constraint. I go to coupling, click continue, select the constraint control point. That means it has to be a control point. That's our reference point. done. Select the constraint region, which is a surface. I click on the surface. I click on that surface again, and I click done. And now I get a menu that says which surfaces I'm coupling to what point, what kind of coupling it is. Default, it's kinematic. The other options are more advanced cases. And I want, if the bottle is pushing down, I want this surface to be moving down, but I don't want the surface to necessarily follow the orientation of the force. So I don't want it to rotate with the force. That means I will ignore the rotation coupling, and I can also ignore the displacement along the other directions. So you have X, Z, and Y. I assume you can easily see that this is, the bottle is going to be pressing down along Y. That means I only need to couple this surface along Y direction, which is U2. So that's the direction along Y. So I even turn off everything. I only leave coupling for U2. That means all the forces will be only affecting the surface downward. And if the surface wants to travel forward, it wants to rotate, it can rotate freely. I hope you understand what I'm trying to explain. So I'm trying to decouple the vector of force from the surface so that the surface only has a force downward, but the surface can move in all directions, because it will need to bend and rotate and twist. So I give it that freedom by only coupling in the force downward. Yeah.
We constrained U2, and U2 is the y-axis, right?
Yes.
Okay, so this force cannot move anywhere.
No, this is not constraining. This is coupling. So if I give a force to this point, that force will be distributed to the pink surface. And only the force along Y will be used and calculated. Okay. So gravity will only go downward, right? You cannot have a X direction gravity. Gravity is only going downward. That's why I'm only using the gravity direction. Okay. Okay. So in case this wasn't a bottle, in case this was like, I don't know, a magnetic body and your magnet was on the side, then you could use also X. If your magnet is next to it and you have a steel component here, then you will use only X. But gravity is only going to be along Y. That's why I'm only using the Y direction. And for this, I can just click OK. There's no need to adjust anything in those. There's always more to talk about. But the necessary step is this decoupling. Okay. And now you see just visually, you see this point in the center being connected with that surface. It's not going to show you too many lines, just few lines to indicate that there is a connection between the point and the surface. Okay. So now I'm done. I have an interaction, I have material, I have everything. I still need the force, and I still need to fix the table. So with the interaction, nothing more to do. I switch to load. And load also includes fixing. So not just the forces, but also fixing. So again, we go downward. These are the settings we add, and this is the list or the boxes where you can edit them again. We start by the force. The force is never gonna be in the initial. That's why here loads may only be created in analysis step. So initial is always the phase before any forces are generated. So we switch to load the bottle. This is a mechanical case, and we want to use a concentrated force of 10 newtons exactly on the center point. So we will load 10 newtons downward, and that will be our bottle. You see, you can use pressure, you can use body force, there's gravity also. So if you have a CAD of the bottle, you can assign it to be water, and then you can add gravity, and then you assign the direction of gravity, and then you can do it like that. But obviously that will take much more time to do. So we stick with concentrated force, and you can say here, bottle. Of course, this is an approximation. Bottle is not 10 newtons, but we even add a bit more and assume it's 10. So bottle of 10, concentrated force, mechanical, continue. And now it says select the point for the load. That will be this yellow, not so visible point. Now that I click it, you can see it. And I click done. Then it says direction of the force. So we want it to be along Y. So that means C2, force CF2. that would be 10. But if I write 10, it will be
10.
upward. Yes, so I have to add a minus, so it switches to downward. It has to be uniform, default -10. The rest can be empty. And the amplitude by default is going to be a ramp. That means if the software starts to calculate, remember this is going to be in 1 second. At the 0 second, it's not going to be 10 Newton. It's going to be a ramp. So it's going to increase slowly until 1 second time. And at the end, after 1 second, the total force will be 10. So it will start with 1 Newton, 2 Newtons until reaching the maximum load. So this by default is what you need, the ramp, but you can always add more other options. So periodic, modulated, decay, whatever. By default, what you have is what you need, ramp. One important step is that if this body, the point, if it is rotating, the force direction should always remain CF2. It should not rotate, right? Gravity will not rotate with the body. That means you should not have this on. It should not follow the nodal rotation. If the node is rotating, the force is always along -10 F2. So never turn this on unless you want it to rotate with it and unless it's not gravity we're simulating. Okay, and when you do this, you'll see a small vector here that says this is a downward force. That means we know we did not do any mistake in the direction at least. Now we're done with load. We can go with mesh. This is generally a bit more tricky part. So by default in the mesh, it's trying to mesh an assembly. And this is why everything still looks the same, blue. And if I try to mesh, it will say dependent part cannot be blah, 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 blah. That means that you cannot mesh generally the assembly. You have to mesh the parts individually, and then you can run the simulation. So I have to switch from assembly to part. And now I see a table, and I can mesh the parts independently. You will see.
I have a question.
Yes.
Shouldn't we encapsulate the table? I mean, the fixing the table in the load.
I can't hear well. So what about the table?
I mean, for the load. I mean, fixing the table during the.
Yes, you're right. You're right. I missed that part. So that's yeah, you're right. I forgot that part. So we're back to this. We still need to fix the edge of the table, right? So if we don't do that, everything's gonna fall down to infinity. So that will be the second menu here: boundary condition, mechanical, symmetry, asymmetry, and incast. We can call this whatever, fixed edge. And continue. Select the surface, which is the back of the table. Done. And default, what everybody does is incast, but it's not necessary actually. It's better to do pinned. Pinned means that this purple surface is not going to be able to move along XYZ, but it can still rotate along the XYZ axis. So incast will make it even more fixed. So pinned is enough, and sometimes pinned will calculate a bit better. So the table still has a chance to rotate at this location, but I don't want it to move. So pinned is, in this case, better than incast, but it's not going to make too much of a difference. Because sorry?
Won't it be a little misleading? Because in this, in the real case, the buckling will not be in the table. It will be in the part. Yeah, but so, here there can be some buckling there.
Yeah, so we don't care about the stresses in the table. So because what we will have this contact and the friction. So whatever we use here is not going to make a difference for the part. It will only make a difference for the table. So we stay with pinned for now. And you see those orange, you see it's fixed. And that's, I guess, all what we need for now. So we have fixed the base of the table, and we have the force, and we have the interaction between the two. So we go back to mesh. We go back to meshing a part. And you see one part looks orange and one part looks green. Green means that it can be meshed as hexahedral elements. That means kind of cubical elements, because the geometry has already kind of a cubical shape, and it is mathematically very easy to divide it into small cubical elements. So to do that, again, we follow this menu. First, we want to know how big should the mesh be, or how small should be the division. and by default, you have to seed the part. We know this is 50 by 50. So the default suggestion is 10 times division. That's why it's 5. And if I click apply, you will see those would be the division. And that for a table, that's much more than enough. We don't care too much about the table to mesh it in detail. Just click apply, okay. And then I click on mesh the part, yes. And now we have the meshed part. So we have this big body divided into smaller hexahedral elements. I'm not going to go into too much details for this, but we'll talk more about the final part or the design part. But those element types, you have two menus to look into the element types. You have the element type here, assign element type, and you have here the mesh control. So in the mesh control, by default, we have selected hex, or it is usually by default. There is also tet. So these are different types of elements. I will just remesh it as tet just to show you the difference. So the hex is a kind of a cubical element. The tet will give you, let me click, will force me to delete the mesh, and then I'll remesh it. The tet is kind of a pyramidal element. So of course, when you have this pyramidal, you have a bit more heavy mesh, you have more elements, and the calculation for, let's say, tet is not as accurate or as good as the hex. So the generally recommended is the hex. It will give you much more accuracy in the simulation, and it will also reduce the number of elements. So if you can always mesh everything as a hex, that is the general preference. So this already is a very simple part, not much to say about it. But besides the type of elements, you have the mathematical definition of element, which is in the element type. I click on it, I can select the entire part, click done. And here we have the general type. It's a standard element. We're doing standard simulation, not an explicit. Explicit is generally for, let's say, dynamic cases rather than quasi-static. It is a 3D stress calculation. There's a long list of other options. For example, if you're doing only thermal, electric, fluid, whatever. But the default is what we need. So standard 3D stress. You have also mathematical description. So if you have a linear description of the element, these cubes are described by the corners. If you switch to quadratic, the cubes will be described by corners and middle points and extra middle points. And that means in the linear, you have a D8R. That means you have 8 points that are describing this cube. If you switch to quadratic, this is a C3D20. So you have 20 points describing each cube. And that means the stresses are calculated at 20 points for the quadratic case. And that means you have much more accuracy when it comes to Poisson deformation, expansion in the other directions relative to compression or tension. And the quadratic is generally much more accurate. For the sake of time now, as a demonstration, maybe I will just stick to linear. And you can always run your simulation with linear. And then if you have, interesting results, then it's good to change it to quadratic and run the simulation again to find more accurate values of stress. So now I would stick to linear. It is even a reduced integration. If you're not familiar with that, you can read a bit on the manual of what reduced integration mean. I'm not going to go into FEM theory now. So, but what you need to know, this is standard 3D linear. And this element is described as C3D8R. This information is very important that you include it in any report, in any presentation. What is your element type? So this is an 8-node linear brick reduced integration hourglass control. If I switch to quadratic, this is a 20-node quadratic brick reduced integration. If I click this off, it goes off, okay? So this is something, whenever you run a simulation, it's very important that you know what this is, and that it is linear, 3D, and a standard. Okay. Now done. Now we go to the part designed by Mike, and you see it's in orange. And whenever something is in orange, that means the default geometry, the default state is not optimal to be meshed or to be dissected or cut into smaller elements. And that generally means you have to do some small adjustments to allow it to mesh properly. And if I try to mesh it without doing anything, I just go to mesh, It says already there's region with some problems in it. It will not, whatever. So I have to improve the part. And this is what you need to learn in Abaqus and you need to practice on your own to be more familiar with, is how do you cut this part into smaller geometries so you can, again, dissect them. So what does that mean? That means you see this flat plate here. I can theoretically, mathematically separate it from the rest, and then I can mesh it. And how do I separate it from the rest? I use an extra menu here, which is called the partition. And if I click on it and I keep pressing my mouse, I get an extended menu for other options. I actually at the moment need the first option, which has, I want to actually separate mathematically this volume from this volume. And I can choose a point and separate along a normal. I can choose 3 points because 3 points will generate a surface, and then that surface will be the separation between the two bodies. And I can also use a point normal to an edge. And in this case, I can use this, maybe I can use point and normal. I want this to be my point of separation and this to be the normal to it. And that means now I have a perpendicular surface. And if I create a partition, you see now it separated this plate from the body. And the color has changed. Now it's yellow. That means the software is more or less accepting this surface to be divided. And instead of meshing everything, I can click down and press and wait. And I get a menu where the first icon is mesh the part. The second icon is mesh the region. So I switch it to mesh the region. Now the button is mesh the region. I select this region that is yellow and I click done. And now I have this yellow area only meshed and the rest is still complaining. So this is where meshing is not an easy thing. It's not like you click a button and you have a mesh. Meshing is a very complicated process where you have to spend a bit of time to improve it, to get a proper part and to run a proper simulation. And you see here, there's a lot of weird shape elements and some of them are very distorted, some of them are not good. And to check on that, you can click on Verify Mesh, click on this area, click Done, and click Highlight, and it will show you which elements are not good. And the color yellow, and here it says warning, yellow, that means those elements are not good. They have very small angles, they have distortion, they are not good elements for the simulation. And to improve them, one general tip is to make them smaller. So to do that, I go to the seed part, which decides the distance between the elements. I switch to a smaller number, 3, click apply. That will generally delete the mesh. So I tell it not to ask me again. Delete mesh, now it deleted it, but you see the dots are closer. I can try to go to 2. This is even closer. You know, I hope this is clear. You go to 5, this is very dense. So it was 6, now I'm gonna go to 3. That's half of the previous value. And then I will again mesh this part. And you see now it looks a bit more homogeneous. It looks more or less better. Then I will again use the verify, click on the part, done, highlight. And now you see there's nothing yellow. So there's no complaints. And it says you have 156 elements, 0 errors, 0 warnings. So now this is a good mesh. Okay, and you see we have a lot more to do. Obviously, this twist part, it's good to separate it from the U part. Again, we can use the same trick of partition, but this time I will select this body and will be invalid. Okay, this time I will use the option of 3 points. So this time I will use 3 points to define the plane at which we separate. And I will use this point, and the one here in the bottom. That means that we will separate the twist from the U, create, and now you see it's separated. And I would call it the software is really happy that this is in green now. It can be perfect hex, and this is in yellow. It also can be meshed. You can keep doing this. You can also cut it from here. You can cut from here. You can keep cutting until you get everything in green. But again, for the sake of time now, I will not do that. I will again mesh specific zones, I will select the center. And you see, this is how it will mesh. I will again use highlight, select it, click done, highlight. And you see there's a lot of yellow. So this will not mesh perfectly. It is okay, but not perfect. So we could need some adjustments for that area. And sometimes the problem can be visually detected. So you see those elements are twisted here. It could be useful to have a different seeding on this side than the seeding on that side. And when I say seeding, I mean those points. So I click here on seed edge, I select this edge, the rest is fine. Only this edge where there is the strong twist, I will adjust the number of seeds from 3 maybe to 2. So I'll have a smaller distance between the dots only for this edge. Click apply, now it's kind of reset, and then I will mesh this point again. This sometimes helps, sometimes doesn't. So you have to repeat those until you optimize. So it's still not perfect, it's still yellow. I'm not gonna spend too much time on it now trying to make it perfect. Yellow will still calculate, it's a warning, but if you have pink, it will not calculate, it's an error. So I will also mesh again the top and mesh the bottom. You see also on the bottom there are some distortions that are not welcomed, let's say, but every place you have a curve, that curve should be at least described by 5 elements. And you see this curve is described by 2. So we need to add more elements here. And again, I go to seed an edge. I select this edge. I click shift and select the back edge here. And I go to the bottom. I click shift and select those 2 edges again. And I click done. And as I said, by number, it says default 2. It has to be at least 5. So I switch them and I force the software to have 5 divisions here. Click apply, you see the 5 divisions. Click mesh, click the area, done. And now you see, this is a much better geometry of division or division method. So now I just improved the part more or less. I improved the mesh more or less. It's not perfect. To make it perfect, I have to spend much more time on this transition zone. And it is, let's say, more or less experimental. Maybe I'll try one last trick. I will go to the seeding. I will switch this to 3 again, as if it was before, and mesh it one more time. You see here you have, it seems to have more elements here, smaller elements here, and larger elements there. So it looks like I actually have to increase the number of elements here, or the size of divisions here, to have more divisions here than that side, because you have this increase in the width. So I will do the seeding again, and I will change the back to 2. That will give me a more homogeneous or more cubical element. Let's do this.
Shouldn't you use forward bias in the sidelines?
Yeah, there is always a lot of methods to improve this. But I don't want to spend too much time now during this recording of the video to correct or improve the mesh to be perfect. So that needs a lot of iterations. So you see now this still has some problems, but we also still have some problems in this area. So I will not deal too much with the back. I just will deal with this area because this is the area that is in contact with the table. And I need it to have less errors because this is where friction happens. So I select those, and I add a bit also, again, the number here to maybe 6. So on the contact area, it's good to have more elements. And then click on it, click done. And you see now you have more divisions here. This is still not perfect. There is one more thing to take care of or to consider. It's that whenever you have a beam that will bend, the number of elements per thickness should at least be 3. And you see here through the thickness, there's 1 element. So this is actually not a good mesh. I have to divide it so I have 3 elements per thickness. To do this now, it will take a bit of time and some trickery. and it will be very heavy mesh. So to easily do this, you can go to Tools, Query, Distance, and measure approximatively the thickness here. I think if I take this point, or there's no other point that's suitable. So I assume also in the CAD, you know, the thickness, but this is something close to 2.7, 2.8 in thickness. And that means if I assign the general mesh size to 1/3 of that, so if it is 2.8 and I use 1, and now I remesh this area, now you have 3 elements per thickness. Okay, so this is actually the minimum, or at least the quantity of elements you should have, 3 per thickness. Okay, so this is kind of like a rule to remember. But what does that cause me is now it's a much heavier mesh. And if I go to highlight, click on the part, click done, and highlight, you see here we have 55,000 elements, and we have 7,000 more or less not so homogeneous elements. And the tip here, it's still non-homogeneous, but I cannot fix that because that comes from the angle that Mike used here. And the only way I can fix this element is by adjusting the CAD file. So as it is now, it's fine. It's not going to be a big problem. But also this is 55,000. This will take some time to calculate. So just for the sake of this simulation, I will keep it as a large mesh, and I will mesh it with the element size of 3 rather than 1. So this is much denser, much larger mesh. And you see again here you have a curve. We have to divide it by 5. So there's a lot to still improve. But for now, I will stop here, and meshing on its own is 1 hour of time or 2 hours just for the meshing. Let's move forward to the final step, which is job. So we go to job, and then we get again this menu. So I'm skipping optimization, obviously. We create a job. We call this load. Again, this is Mike's file. So the job is important to name it because it will be an independent file at the end that you can save and share and load and whatever. So this is load Mike v1 5/1 2021. Okay, and we only have model 1 in the list. That's why you only have a selection of model 1. And continue. I will not talk too much about this, but let's call this load. Default is fine, so it's a full analysis, whatever. One thing you should consider here is parallelization. So how many processors do you have? In my PC here, I have 8 processors. So I can use multiple processors. At least I will use 4. So I reduce the time of calculation by using more processors. And in some cases, if you have a very capable GPU or graphic unit, you can also use your GPU. So by default, I'm just adding four processors in the list. There's much more to talk about, but that's not in the scope of what we're doing. But what's important is precision. By default, it is single, and this runs very quick. But when you have results and your simulation is okay, and you want more accurate data, you should copy the job, switch to full, and run it again. And full just means how many digits after the comma when it's calculating. Single precision will ignore some of those fractions. A full precision will barely ignore any fractions, and you have much more accurate values of force, values of displacement, or whatever. But for time's sake, and especially when you're doing your first simulation, you want to see your initial results, you keep it at single. So whatever you need to change in job is precision and parallelization for now. Click OK. You will have in this long tree at the end the job, and this is, if you click here, you have load Mike, and what you need to do to run it is just right click and click submit. Okay, for now, any short question that I can answer?